All right, so for today, I'll be talking about different functional colloids you can make using thiol-ene chemistry and some of their possible applications. So for this speech, I'll be going over the thiol-ene reaction, a couple different ways to make colloids, both heterogeneous methods that are currently used, and then I'll be talking about my own research. So in this case, we have core shell materials made from Pickering stabilization with silica nanoparticles, so you have a different surface chemistry than a core chemistry. Then I'll be talking about the oxidation of thiols to make hopefully gels, and then heavy metal sequestration to absorb metals in solution for drinking water cleaning. Then I'll talk about some conclusions and future work. The thiol-ene reaction isn't a new reaction. But in recent years, it's seen a resurgence of use since you can use it for polymerization mechanisms. So in this case, you can see this is an addition reaction. We have an initiator that takes a hydrogen from a thiol to create a thiol radical, which then adds over an ene group, and then that can go on to extract another hydrogen. This is interesting because even though this is an addition reaction, which generally is a chain growth mechanism for molecular weight, this is actually a step growth mechanism. So in this case, it's much easier to functionalize these types of polymers because if you leave a little bit excess of one of the two moieties, you get that back at the end. So if I add in 50% extra thiol compared to the ene, I should end with 50% extra thiol left over in the end reaction. This is a very robust reaction. You get near 100% conversion with very little inputs, normally just light or some mild heating. On the right, you can see the different reagents that we normally use. So if you want very cross-linked polymers, you can look at TTT and PETMP. Whereas if you want linear polymers, you can look at TMPDA and HDT. So you can get all varieties of different polymers using the same chemistry. The two different mechanisms for creating colloids that I'll be talking about are both heterogeneous methods. These are the emulsion polymerization and the suspension polymerization. So as you can see, you would currently add your monomer to the continuous phase with some type of emulsifier like a surfactant. Mainly the difference between the two is what type of initiator you'll use. So in emulsion, you generally use a continuous phase soluble initiator. This then will initiate little bits of your monomer that are soluble within the continuous phase, which can then diffuse into the micelles to start your polymerization. This can then diffuse from larger monomer droplets into the smaller ones until you reach a stable size. These can be monodispersed, and they're generally very small, like 100 nanometers to 1 micron. The suspension polymerization is almost the same thing, but you'll be using an oil-soluble initiator instead. So in this case, you don't have the diffusion. You do have some mass transport, but essentially you are polymerizing the droplets instead of having this diffusion mechanism between droplets. You get generally much bigger particles that are fairly polydispersed. So as I've written down here, typically 1 micron or higher. So of course, why would you make polymer colloids? There's many different reasons why. There's many things where you've seen in literature, drug delivery vehicles made out of colloids. You can coat other materials for such as scratch resistance. Water treatment, I'll be talking about a little bit. This can be used as fillers. We commonly use them as house paints and house adhesives. So as I talked about the Pickering stabilization, this is to create a particle that is a composite that has one functional surface and a different functional core. So in this case, we'll be having silica nanoparticles as the surface, so you'll have hydroxyl groups you can react with, whereas the core will be polythioether particles. In this paper, we tried a few different co-surfactants, which you can see at the top right. However, our monomer system was very cross-linked of TTT and PETMP. You can see at the bottom, these are around 1 to 3 microns. We do have some aggregation of the silica particles at the end, so it's you see it as a very polydispersed sample. You can see some of those aggregates right here. In this case, we use cetyl alcohol because of its alcohol nature on the surface. This we assumed would be able to hydrogen bond the silica, which you can see is successful. We have a much lower amount of silica needed to actually stabilize these particles. It also tightens the distribution. Whereas toluene is very nonpolar, So we have the opposite. We need to add essentially double the amount to get that same distribution, which makes sense because there's no reason for the silica to bind if it's less polar. You can see right here that all of our TGs are essentially the same as the bulk polymer, which makes sense. We're putting these on the surface. We're not chemically incorporating them into the polymer, so they all should have the same TG, other than the artifact of hexadecane, which has a significant phase separation with the monomer system, so you have the melt temperature of hexadecane in there. And you can see on the right, for ATR, we have near full conversion of thiol and ene, so successfully 100% conversion. The next one we'll be talking about is what I was saying when you can add in excess of one moiety and get it back at the end. In this case, we're looking at leveraging the thiols. So when you add, we already know in the body, when you oxidize thiols, we get disulfide bonds. So in this case, we want to try and leverage that effect to create gels within solution for either encapsulation or drug delivery. So our hope is that we can add an oxidant, get these purposely aggregated, then have a reductant slowly reduce it and release things from inside the gel. For this, we decided to use a model study. This was just taking PET-MP, which is all just thiols, adding it as 10% in a continuous phase with 10 millimolar SDS, and then oxidizing it with our first solution of 1 mole % sodium iodide, and then adding in equivalents of hydrogen peroxide. As you can see on the left, once we get up to about 6 equivalents of hydrogen peroxide, we have near full conversion. On the right, you can see just PET-MP being emulsified has a huge distribution. This acts almost like emulsion, where you have a much narrower window after polymerizing it. In this case, creating the disulfides, you have a very small distribution. So of course, heavy metals are bad for health, and sometimes they make it into drinking water, as we've seen in the news. In this case, we know that thiols are a nice soft Lewis base. They have a very high atomic radii. So we want to leverage this to get very soft acids like lead or mercury from solution. So for this, you can see this is 50% extra thiol using PET-MP and TTT, like the Pickering emulsion. So you can see we start with some kind of small particles on the left graph, and they get much bigger after being in contact with the lead solution. You can also see that after thiol, we have a much higher mass that is left over after decomposition in TGA. So of course, for conclusions, the Pickering stabilization, you can see that cetyl alcohol creates a much more stable dispersion. So we have a tighter distribution, all generally near one size. We still have some silica aggregates. For the oxidation, you can see that it's successful in a biphase system to use aqueous-based chemicals of sodium iodide and hydrogen peroxide. We got near full conversion. Lastly, for heavy metal sequestration, you can see that the TGA took up extra mass, which is important because after we burn off all of the polymer, what should be left is the lead. So we definitely have some uptake of lead. So for future work, Pickering stabilization is essentially done for now. You can see at the bottom, we actually produced a paper from this last year. You can check it out. The reference is at the bottom of the slide. For the other two projects that I mentioned, the oxidation of these is successful. You can see near full conversion of thiols. However, we didn't do this on a particle basis yet, so the next is to take the particles we've made that have excess thiol and, of course, oxidize them and see what the size increase is. For this, we're planning on starting with 50% excess thiol and working our way back to seeing what the difference, to see if there's a different size increase for each amount of thiol. For heavy metal sequestration, we use SDS as our stabilizer, so it's a base 2. It can bind metals, so we're not exactly sure its effect on binding metals right now. So we have to try using non-ionic surfactants or even cationic surfactants to see if we have a control with the cationic, to see if we have any absorption, and then non-ionic to see if we have near the same amount of absorption to see what the actual effect of this SDS is. So we definitely have some work to do on both, but both look like they're heading towards successes. Thank you for listening.